Hi all, I am Bhavya Menon from Department of Electronics, MES College, Marampally.
Welcome back to the transmission line. Now we are going to study in detail about two-wire parallel transmission line. So this is a simple diagram of a two-wire parallel transmission line. We have already discussed that they are having two conductors. They are separated by a certain distance S. Okay, and here we have a source and here there is a load denoted by Z. So a two-wire transmission line is a symmetrical, that means it is balanced line, that's balanced transmission line with two conductors of equal size and shape. These cylindrical conductors have a diameter D separated by distance S from center to center, and these supporting mainly TEM wave, that is transverse electromagnetic wave. So transmission line always supports the TEM wave. Okay, and here they are mainly used for power transmission in telephone lines, TV signals, etc. Usually, there is a balanced transmission line which is limited to frequency below 500 MHz due to radiation losses. They convey the electrical signals between two points separated by an applicable distance. Here L is the total length of the transmission line, D is the width of the transmission line, and S is the distance between the two transmission lines. So the above diagram can be drawn into an equivalent circuit in such a way that it consists of four parameters, which is resistance R, inductance L, capacitance C, and G, which is the conductance, shunt or leakage conductance per unit length. So, four parameters which is mainly used in a transmission line are R, L, C, and G, that is resistance, inductance, capacitance, and conductance. And this equivalent system or equivalent circuit can be again redrawn as by the following measures. These quantities, resistance, capacitance, conductance, etc., they can be calculated with respect to length of the conductor, and we get two different values such as series impedance and shunt admittance. Series impedance denoted by Z, that's equal to R plus J omega L, and shunt admittance denoted by Y, that's equal to G plus J omega C. The inductive resistance has a greater value than that of the resistance with respect to the radio frequencies. And on the other hand, the value of capacitive susceptance is also much more than that of the shunt capacitance. So, these all the quantities are working along the length of the line. So, if we can ignore R and G, then we can consider the circuit as a lossless circuit. And in radio frequency signals, C, capacitance is very much greater than G, and inductance L is very much greater than R. So this becomes an LC circuit where Z0 is equal to root of L by C. How we are getting Z0 is equal to root of L by C? We can see it later. Now, when we are taking into account this L and C alone, the above equivalent circuit is shortened or becomes simplified and can be redrawn in such a way that it becomes an LC circuit. Okay. So, and from this we can calculate the characteristic impedance of the transmission line. That is, if a uniform lossless transmission line is considered for a wave traveling in one direction, the ratio of the amplitudes of voltage and current along that line which has no reflections is called a characteristic impedance. That is, it is the impedance measured at the input line when the length of the transmission line is infinity, and that is denoted by Z0. Now we can see how this characteristic impedance is measured. That is, Z0 is equal to square root of voltage wave value by current wave value. So that is equal to, we have already seen that is equal to square root of series impedance by shunt admittance. That is, Z0 is equal to root of Z by Y. Then we can substitute the values of Z and Y. We get Z0 is equal to square root of R plus j omega L divided by G plus j omega C. And for lossless line, we have already seen that it becomes an LC circuit when R and G is ignored. So we get R0, or that is the Z0 is equal to square root of L by C, where L and C are inductance and capacitance per unit length. Okay, so the characteristic impedance can be defined as Z0 is equal to root of R plus j omega L by G plus j omega C. For the lossless line, it becomes square root of L by C. And that's about the two-wire parallel transmission line. So, in two-wire parallel transmission line, we have seen the diagram of a two-wire parallel transmission line. Its equivalent circuit consisting of R, L, G and C. And for the lossless circuit, in RF signal, we can take it as an LC circuit removing G and R. And from that we derive the value of characteristic impedance, and that is the impedance measured when the transmission line length is infinity. This impedance measured at the input when the length of the transmission line is infinity, and that is defined as Z0 equal to root of R plus j omega L by G plus j omega C, and that is equal to square root of L by C. That's all about the transmission line. And we have seen that there are four parameters of the transmission line. The four parameters are resistance, inductance, capacitance and conductance. And here resistance and inductance together forms the impedance, capacitance and conductance together known as the admittance. Okay, and these are the mainly four parameters of transmission line. As we all know, what is resistance? We all know that is the resistance offered by the material out of which transmission lines are made will be of considerable amount, and especially for very shorter line. Here we are having the ohmic loss defined as I square R loss, and the resistance is mainly affected by temperature and frequency of the current. And here the more current flow towards the surface of the conductor, flows less towards the center, which is known as the skin effect. Second, we have the inductance. We know what is inductance is. It's a magnetic flux is defined by this inductance. That is, current flow in the transmission line induces the magnetic flux. When the current in the transmission line changes, the magnetic flux is also changing, due to which the EMF induced in the circuit. And the magnitude of inducing EMF depends upon the rate of change of flux. These parameters can be defined as the inductance of the line. And capacitance, that is, air is acting as the dielectric medium, and the dielectric medium constitutes the capacitor between the conductors, and it is having the property to store the electrical energy or increase the capacitance of the line. Okay, and we know that capacitance C is equal to epsilon I by D. When D, there is a distance between the plates, increases, the capacitance decreases, and vice versa. And last one is the conductance, and that's normally denoted as shunt conductance. Air is acting again as a dielectric medium between the conductors, and when the alternating voltage applies in a conductor, some current flow in the dielectric medium because of dielectric imperfections, and this current is known as a leakage current, and leakage current depends upon the atmospheric condition and pollution like moisture and surface deposit. And shunt conductance is defined as the flow of leakage current between the conductors, and is mainly represented by the letter Y and is measured in Siemens, that is the opposite of or reciprocal of ohms. And these are the mainly four parameters, that is R resistance, L inductance, C capacitance, and G conductance. Hope you all have understood this. Thank you.